So with this packet, don't try to say, hey, I'm just going to try to solve it all by myself, do like that, because I want you. There's a specific way I want you to solve these. And if you go about trying to do it your own way, try to figure out your own way. I'm not saying that you can't. I'm not saying that you're not smart enough to do that. When we get into more complicated situations, it's going to be good to have a baseline that we're doing consistently over and over and over the same way. I'm trying to figure out which marker I had and which one was the darkest. I think this was the darkest. It is the coldest, so it is the darkest. I figured out my first year of teaching when I'd reach into a basket of markers, the one that was coldest was usually the darkest. It has something to do with like the ink not holding on to heat very easily. Oh, whatever. They were like, hey, that's interesting. And, or actually, you know what? Nobody said that. So it was all good. I found it interesting. Instead of having to make little marks on the board and figure out which one was the brightest. So I am going to, I'll write this up here first. So what you see here, we're going to start with number 2 first. This is a word problem. There's going to be obviously numbers inside there. There's going to be context clues. And what you see over here is I put this here for our packets. And this is not where your answers go. This is not where the answers are supposed to go. This is just showing you where to kind of place your place the variable so that when we go picking the equation, it's a lot easier. The idea is that you not just read this and figure it out in your head or try to look at the equation and do it all at once. So 2 words that are very important, I guess our first context clues, are the words from and the words to. So when you read a problem that says from something, some amount of measurement, to something else, the from is very likely giving you your initial value, or it's not like it is giving you your initial value, and the final is giving you your final. So if I say I'm going from 10 to 20, that means I'm going from a lower 10 up to 20, I'm speeding up. If I go from 20 to 10, that would mean that I'm slowing down. So you might want to jot that somewhere. The other thing we want to avoid in physics here is being what I call a number hunter. So a number hunter is somebody that ignores the context of what's going on in the problem, and they just say, they read through and they say, 61, 2.5, yeah, it doesn't really matter what's going on. They try to figure out the problem themselves, and that gets very, very complicated, especially when we get into multiple dimensions of moving stuff. So first thing we'll do is, first of all, before we start this, these 4 equations are only valid. Yes, they're the equations of motion, but they are only valid for constant acceleration, okay, or uniform acceleration. If we have some acceleration that is not constant, meaning it's change in acceleration, then you have to use calculus. Basically, what's the difficult thing for the last probably 3 or 4 weeks for AP Physics is that they're having to learn calculus. Basically, at the very beginning, they have to start learning calculus because that's basically what they're doing in that class. The problem is they haven't learned the calculus in their calculus class yet, so they're having to sort of take a boot camp or a crash course on just the basics of like polynomial calculus so that they can do the minimal problems, because if they can't do that, then they'll be stuck basically in chapter 1 forever. So we will always, in this class, in regular physics and non-AP and non-calculus based physics, the acceleration will always be constant. It'll either be a constantly 0 acceleration, which this is constant velocity, or it'll be a constant non-zero acceleration. So if something says it's accelerating uniformly at 2.5, it means it's doing that indefinitely and is not changing that. So to remind you what each of these values here mean, and I'll actually write them off to the side so that for my recordings they can actually see that. So you don't need to do this. That's so it can actually be seen. So the first one there is displacement, delta x. Then VI is initial velocity. VF is final velocity. T is time, and A is acceleration. So we'll go ahead and read through the problem here. It says an engineer must design a runway. An engineer must design a runway in order to accommodate airplanes that must reach a ground velocity of 61 meters per second before they can take off. These planes are capable of being accelerated uniformly at the rate of 2.5 meters per second squared. This underlined sentence here is not in your packet. I didn't have time to change it, but it doesn't say in here, but we're assuming that the airplane is starting out. They're not like taxiing on there and then they start going, they're starting from rest. So you can just indicate that it's starting from rest. So the first thing is asked is how long a time will it take the planes to reach takeoff speed? Then, once we know the time, the second question is, what must be the minimum length of the runway? So the minimum length runway is just whatever delta x is there. So first thing we want to make sure is everything is in meters and meters per second squared, which it appears everything is. Now we want to start identifying, start writing down things that we know here. So what are some things that we know that the was telling us? Yeah?
It can accelerate at 2.5 meters per second.
Yep, 2.5 meters per second squared, or meters per second. 2.5 meters per second squared is there. So you'd want to fill that in your A part. Once again, I'm only doing this for the online video. What else do we know? Yeah.
The final velocity has to be 61 meters.
Yep, 61. How do we know it's 61? How do we know? What in the problem tells us is that?
It has to be going 61 to take off.
Yeah, oh yeah, that, and also that it starts from rest. So it can't be the initial. So yeah, it's obvious. I'm just trying to illuminate it. So the initial is 0 meters per second, and then the final is 61, because in the whole takeoff sequence, that is what it needs to finally take off. And we're trying to figure out what is the time. So yes, we need to know what the length is as well, but we'll go ahead and ignore that until we solve for that. And so now that we have 4 of these variables, let's travel over to our toolbox here, our equation box. This is acceleration, so we're in here. So go ahead and look through 1, 2, 3, and 4, and raise your hand with which number. So tell me which number we would use first to just find time. We're trying to figure out what the time is here. Okay? So we have VI, we have VF, we have A, but we don't have T. Should be the second equation. Okay? So VI, VF, A, and T. And notice, for something that's going to take place in just a second, that's the only equation that we can use in order to find that time. So what I ask you is that you minimally write out the equation, because a lot of mistakes happen when people are trying to not only put the equation in but plug the numbers in at the same time. Things like missing squares or missing variables altogether. So VF equals VI plus AT. I'm totally fine when you plug in the numbers that you don't plug the units in. I think that kind of makes things a little busy. So what I mean is you can just plug in 61 equals 0 plus 2.5 times t to figure out what that is. Let me adjust this right quick. Okay? And to solve for time, I would just take 61 divided by 2.5. And what do we get for that? 24.4 seconds. Good. 24.4 seconds. Okay? And we want to ask ourselves just some questions like, does this make sense? Okay? Sometimes it'll be a very specific, like, does this specific number make sense? The fact we got 24.4, well, first of all, it's my responsibility, if I'm going to ask you to ask yourself, does 24.4 seconds make sense for a liftoff? What do I have to be responsible for when I create these problems? That the answers must make sense, right? It wouldn't be fair for me to say, hey, does that make sense? And I have just this dumb numbers up there, and let's say that the correct answer was like 0.1 seconds to take off, and I ask you, does that make sense? And you're like, no, it doesn't make sense, but it's actually the correct one. So I have to make sure when I'm developing these problems that I make the right answers within the realm of possibilities. Yeah, it's not just an instantaneous, explosion into the sky. So 24.4 seconds, surely you can imagine some plane, and maybe a little slow, some plane eventually taking that long. But if you had something like seconds and it was like 3 years to take off, then you're like, okay, well, that doesn't make sense. And what I'm trying to teach is that if it doesn't make sense, for you to back up and say, wait a second, there's an error somewhere in here. So I have to make sure that I tell you that this is within a realm of possibilities. So the next thing is we're finding is what must the minimum length be. Now, you don't have to write this in here. Once again, this is not where I'm looking for your work. Just wherever your work is, put a box, and that answer should be close to your work. It makes it easier to grade. It makes it a heck of a lot easier to do partial credit if there was an error. If I'm having to search for your answer somewhere, I'm probably not going to spend a lot of time trying to find partial credit. So notice we could have only used the second equation on that, but now that we have time, it says what must be the minimum length of the runway be? Okay, we need to find delta x. Can we use the first equation? Okay, we have VF, we have VI, we now have the times, that's one. Can we use any other equations? You can use 3. We have VI, we have time, we have acceleration. What about the fourth equation?
No. Well, yeah.
We have VI, we have VF, we have A, we're solving for delta x. So what I'm going to show you is I'm going to show you that pick whatever equation you want. I'm going to show you the work of all 3 equations to say that if your time is correct, you should have the exact same answer for all of them. So I'm not going to write out the equation just because of the amount of writing this is going to take here. But for the first equation, delta x equals 1/2 0 plus 61 times 24.4. So somebody said, oh yeah, well why would you use number 4? Here's one of the reasons in just a second. So we'll see what we get for the first equation. The third equation, 0 times 24.4 plus 1/2 2.5 times 24.4 squared. And then the fourth equation, 61 squared equals 0 squared plus 2 times 2.5 delta x. So we'll see what we get for each of these answers here. Who used the first equation? What did you guys get? 744.2. I also got that. Anybody use the third equation? Probably not, because it's not fun. But if you use the third equation, you get 744.2 meters. You don't believe me? Solve yourself. And for the fourth equation, you also get 744.2 meters. I'm not saying that you have to use all 3 equations to prove that it's 744.2. What I'm trying to show that when we only had minimal information, there was only one tool, one equation we could use. But now that we had that extra information, suddenly the rest of the toolbox opens itself up. See the analogy? So let's say that you were not confident in the time you had. You were like, I'm not really feeling well today. I'm not really sure if A is correct. What would be the best equation to pick if you were not sure if your answer for your time was correct? Fourth, why? Why?
Because it doesn't deal with.
It doesn't have time in there. So I'm not saying you need to live your life always second guessing yourself. But if you really weren't sure, like, hey, you solved this and you're like, I don't really know if that's the right time, maybe I messed up, you can always pick, if you always want to just double check, you can pick an equation that doesn't have, for example, in this problem, time, and you should get the same answer. If we didn't get the same answer, then that would mean, ideally, if we solved it correctly, that your time was not correct. So sometimes there's strategies in picking equations because you're not relying on other data to set you up for that. Okay? Let's go ahead and look at number 3 together. Sports car. Sports car. So I haven't looked at the quizzes yet, but I'm doing this one because I just want to make sure that we're kind of still practicing a little bit the unit conversions. Okay. Number 3, a sports car accelerates from rest to 95 kilometers per hour. We have to convert this to meters per second. It does all that in 6.2 seconds. What is its acceleration in meters per second squared? And also, how far does the car travel in this time? This is basically like a 0 to 60 kind of race here. So we need to figure out, first we need to convert the 95 kilometers per hour into, so 95 kilometers per hour. Hour. Okay. We should know that a kilo or kilometer, 1 kilometer is 1,000 meters. So kilometers. And then to cancel out the hour goes on top. Yes, 1 hour is 60 minutes, 1 minute 60 seconds, but 1 hour is 3,600 seconds. So we take 95 times 1,000 divided by 3,600. We don't get an exact number here. We round out to 2 decimal places. It's like, it goes out to like 26.387, something like that. So what does that round out to when we have 2 decimal places? 26.39 meters per second. The question was asked, do we use that rounded value when we're calculating? Yes, please use the rounded value for that. Now, here's a good strategy. Once you figure out that this is 26.39, go ahead and cross out 95. You don't want any possibility that you would accidentally use 95. I've seen this many times, especially in problems where there's a lot of converting going on before the problem, like when we do radians and degrees and rotation, where somebody in the heat of battle solving the problem, they're like, what is my velocity? And they look back at the original problem and they see 95 there, and they put it 95, even though they already converted the problem. Guess I have to erase these. There's some problems that we're going to do when we get to rotation where everything will have to be converted in and then out. So what's something that we know? Yeah. Time is 6.2 seconds. Okay, what else we know? Yep.
Initial velocity 0.
Yep, so we have those words there, that from and then to. So from rest means, yep, the initial is 0 meters per second, and final is not 95, but our 26.39 meters per second. And what we're trying to find is acceleration. Now, the reason I picked this problem is I wanted to make sure we were doing the conversions right before we move on. But the unfortunate part is we're basically using the same 2 equations we did in number 2, but that's just the way it goes. Don't assume that that's always going to be the way. It is not. It just happens to be like that. So if we're looking over here, we have VI, we have VF, we have T, and we're trying to find A. So once again, we're going to use the second equation. Now, it really doesn't matter. If you would say, hey, I want to find delta x first, you could certainly find that. But I set up this initial worksheet to kind of give you the easiest path through. So go ahead and write out the equation, even though we wrote it out before. Because the more times that you write it, the more times you're going to get comfortable with what it's going to look like. Okay? You don't have to memorize it, but it'd be awfully nice if you didn't have to look up there for every single time for what the equation was. Okay? Go ahead and plug some stuff in. So final velocity is 26.39. Initial is 0. Acceleration is the unknown, and time is 6.2. So this is also going to be a rounded value. Is that 4.26? You guys should be calculating at this test. You don't want the quiz to be the first time you'd ever calculated these problems. So 4.26 meters per second squared. Now that's hard. It's very hard for us to kind of rationalize how much acceleration that is. Tomorrow when we talk about number 8 talks about G load. So like, if you've ever been on a roller coaster, like the most a roller coaster I think pulls or pushes on you or pulls away from you is 3 Gs. So 3 times your body weight. If you were in a car accelerating 1 G, that's 9.81 meters per second squared. So that's less than 1 G. This would probably feel like what it feels like if you're basically getting onto the highway. That's kind of it. You're not accelerating in 3 seconds. Because 26.39, a rough estimate here is you multiply that times 2 to give you an idea of how fast that is in miles per hour. So it's 2.2, but that's about maybe 55, 60 miles per hour. So you're going from 0 to 60 in 6.2. Certainly not game-changing speed there. But it's not like a Bugatti Veyron or something that does it like in 3 seconds or something like that, or 2 seconds or something insane like that. Okay, and once we have that, how far does this car travel in this time? So we go over here. We can certainly use whatever the other equations we want, but most people would say at this point, what's the easiest equation out of 1, 3, and 4? Probably 1 to use, okay? So you can certainly pick whatever. That's why when I do keys for quizzes and tests, I have to solve it like the 3 different ways in case somebody chose to do that. It's certainly whatever you choose to do. So the first equation, delta x equals 1/2 VI plus VF times T. 1/2 0 plus not 95 but 26.39 times our 6.2 seconds. And what is it? 81.81 comes out to. Okay, which you know, I'm not familiar with doing trying to accelerate my car as fast as possible, but I'd probably say that a length of the football field in order to get up to 60 miles per hour is not out of the question. So it's important that you guys are asking questions. I always say to each of the classes, the honors classes, your class is when you need to be asking questions. But why don't you think people ask questions in an honors class? Yeah.
They get embarrassed.
Yeah, they want to be like, hey, I might be the only one that doesn't know. Okay. Rarely is that the case. Rarely is that the case. Sometimes somebody will ask a question, and other people are like, why would that even matter? And I'm like, oh yeah, good point there, and I'll talk about it here. And then a lot of times I'll talk about it each period after that because it was such a good question that it helps everybody else. But a lot of times what happens is, let's say that I'm writing fast and I make a mistake or something like that, or there's something that's kind of troubling everybody, and everybody's kind of like, what's kind of going on here? And then it takes that one courageous person to raise their hand saying, I don't really understand what you did there, or shouldn't that be a 5 instead of a 2? And everybody's like, oh, thank you. I'm glad somebody asked that question. That's really what tends to happen. The worst thing that can happen is that if you have a question, there's something, maybe there's an error here, or there's just something that doesn't make any sense. I've had in the past where, for example, here, I was thinking about something, I wrote like 18.18 meters or something like that, and the student is just like figuring out, how does that work? Why is that there? And they don't say anything, and it's making everybody confused, and nobody says anything. The bell rings, and they walk by, they're like, oh yeah, by the way, that should have been a 5. See you tomorrow. And I'm just like, that could have helped if I had seen that, or, hey, I had this question here, why didn't you ask it in the beginning? So always important to kind of bring that up, and it's not judging. I mean, are there stupid questions? I think there are stupid questions, but sometimes they're funny and they lighten up the mood. But other times, most questions are good questions because you're trying to figure out what you don't know. So the last thing we'll look at here, we're going to look at number 7 together. And you kind of get an idea here. I'm trying to pick a couple that are a little bit different from each other, so that when you solve the ones on your own, you kind of had a good mixture of different types of problems. Now for the online videos, when we do some problems later, doing all my work in this much area is not going to work, but we'll figure something out. Like some teachers that have stuff all over their board and only have like a tiny little part to actually write on, I don't know how they do that. So I guess they do show PowerPoints. So not a big believer in showing math on PowerPoints, unless you're maybe actually writing on it. But anyway, let's go ahead and read through this here. In coming to a stop, a car leaves skid marks 92.5 meters long on the highway. Assuming an acceleration of -7 meters per second squared, find the speed of the car just before braking. Sometimes in problems it helps to draw a picture to kind of figure out what's going on here. It's slowing down, but we're not given the normal information here. So here's my introduction to, here's your introduction to me drawing here. So hopefully it's everything you thought it would be. That's not a bad car. If you don't recognize the design, it's because it's a prototype, so it's still in development. So you see it on the road next to you, you're like, there it is. It was right. There it is. Super. So what we have here, the car is coming to a stop. We're not talking about something speeding up or slowing down. And also in physics, we don't use the word deceleration, really. If we want to say that it is slowing down, so we'll talk about this more tomorrow, because a negative acceleration doesn't necessarily mean that you are slowing down. Go ahead and look at me up here. If I'm moving in the positive direction here, and my acceleration's in the opposite direction, what do you think is going to happen to me? It's going to slow down. But what if I'm moving in the negative direction and my acceleration is also in this direction? I'm going to speed up. So you can't just say, oh, that means it's slowing down. Why is this slowing down? Because it was moving in the positive direction. It moved a positive distance or displacement. We'll talk about that and how whether you're speeding up or slowing down depends on which direction you were moving in the first place. So what's happening here is that it's coming to a stop, and you have basically these skid marks here that are your delta x. So you have your car there. What are some pieces of information that we're told?
Final velocity.
Final velocity is what?
0.
0. It says it comes to a stop, or coming to a stop. Okay? What else? What is delta x? 92.5? That's a weird way of telling you how far it traveled, but it's one of those sort of, evidence-based that it's gone that far. Your skid marks came from your car. Now, this is on the verge of not really making sense. If you're traveling, you hit the brakes, and it takes you 92.5 meters to slow down, you might be thinking you're going fast. -7 meters per second squared is not really that fast. It would almost be like, this is where maybe not the most realistic thing. You're kind of going along at a normal pace on the road, and then you lightly tap your brake, and then for some reason you lose grip on the road. You skid for a football hoop. That's kind of unrealistic, but it could happen. You have the worst tires in the world if that's what happens. They must be made of butter. So
Just smooth them down very flat so that you get
exactly, like smooth them down all the way. What else do we have? So we have the acceleration, which is -7. And what we're trying to find is the speed of the car. Now notice, it doesn't ask us for the time. You don't need to solve for every single one of these. The only reason we did in the other problems is because they asked us for several things. If it doesn't ask you for the time, you don't need to solve for it. I mean, I guess you could if you wanted to kind of give yourself more evidence that your answer is correct, but there's no need. There's enough information. As long as you have 4 variables, there's an equation over there that will allow you to figure out which you need. So we go over to our equations. And go ahead and take a look at what we have, delta x. Trying to find VI, we have VF, we have A. Go ahead and raise your hand which equation would make sense for that. Sometimes people are like, and then they see their friends and they're like, yes, there should be a fourth equation. We're not given time, and we're not solving for time, but we have everything else here. At least when I say we have VI, it means that we're being asked that we're solving for VI here. So, yep, we're going to use our fourth equation. VF squared equals VI squared plus 2A delta X. So we're trying to figure out how fast the car was going the moment it started to brake. So final velocity is 0, VI squared, which we don't know, plus 2 times negative 7 times 92.5. Now there's some negatives that we have to take care of here. You can do this a couple different ways. I'm gonna subtract VI over here and have negative VI squared. What's 2 times negative 7 times 92.5?
Negative 1,295.
Okay, that's what I thought, yeah. So there's negatives on both sides. I don't want to square root yet, so I cancel out those negatives. Now that I've done that, I can square root. So VI comes out to, what is this?
35.99.
Yep, 35.99 meters per second. Units are extremely important. 35.99 meters per second. Which, if you take the estimation about how many miles per hour, multiply it times a little bit more than 2, it's about 36 meters per second times 2, which is 72. It's about 75 to 80 miles per hour. Okay, so if you were going 80 miles per hour and it took you a football field to slow down, which is outrageous, then your tires are horrible. They would probably be degrading, and when you got to the end, you would just be on your rims if that was what was happening. So okay, and so that's it. So the question is, do we have to solve for time? No, we don't have to solve for time. We're done. If it asks to do it, we do it. But we certainly do not have to solve that. Questions about those? The last one we're going to look at is number 4, but just the very beginning, because number 4 is one of the ones you'll have to work on. This is just to kind of show you, it's giving you some information in a different way, and it's teaching you sort of, don't be a number hunter. A number hunter takes disregard for any of the context of the problem and just sees numbers and it assumes that it must be what they think it is. So. The idea about building this frame, like, well, this seems kind of excessive, we're going over all this. Well, when we start adding in more variables and, hey, not only are we moving sideways, but we're moving up and down at the same time, it's going to be really nice to have a framework of not only what's going on horizontally, what's going on vertically. So we'll look at number 4, and if you were, let's look what a number hunter would see here, okay? A number hunter would look at this and say, okay, looks like I got 110 meters, that must be my delta X. I got 5 seconds, so wait a second, I got 4 seconds here. I guess I'll just take either one of them, doesn't really matter, or I'll just add both of them together, which I've definitely seen. They're not paying attention to the context, and this is really different for this problem. So it says, a sports car moving at a constant speed travels 110 meters in 5 seconds. Remember, these are not constant speed equations, they are constant what? Not constant speed, not constant velocity, constant acceleration. So something is happening here before it starts to accelerate. Okay? If it then brakes and comes to a stop in 4 seconds, what is the acceleration? We have to realize here that there's basically a car that's going along here. It is going 110 meters in 5 seconds. Basically, the real problem actually starts when? When it starts braking. That's when we can start using our 1, 2, 3, 4 equations there. So we have to think about, what is this information? If it's not used in our acceleration, what is that trying to tell us there? Which velocity? Yeah, it's telling you the initial, because we also have a constant velocity equation, which is your total distance divided by your total time, okay? So 110 meters in 5 seconds is telling you that your speed or your velocity at that is 22 meters per second. So it's 22 meters per second at the very beginning of the problem, so that's telling you your initial velocity is 22, okay? So realizing that this part of the problem right here is separate from the rest of the problem, it's kind of a helpful hint to have. So this is obviously Wednesday, 5th period is longer, so if you choose to work on problems, obviously you're going to have a longer amount of time than other classes would. But by Friday, so Friday we're going to finish up not only the notes, but by Friday you should have these problems done. 1, 4, 5, 6, 8. We're going to do 9 and 10 tomorrow because they're much higher level ones, more like approaching, I don't know, extra credit slash, I don't want to say AP level. I mean, we're kind of at an AP level. Yeah.
I'm concerned about my answer on number 8.
So that card's.
Let's see here.
I mean, I'm not sure I'm right. It seems like a lot.
Okay, let me go ahead and pause this here.